Who has not used ChatGPT yet? Anyone? No. Okay. If you asked that question a year ago, that would be a very different picture. So everyone knows the interface a bit, right? So you can ask questions, you get an answer. I didn't do that, so what's the question? This is part of the lecture. Please introduce yourself and okay, amazing. Thank you. So again, I'm very fortunate that Max actually prepared the slides mostly for me. Tanush also helped a bit. And I'm only here for presenting stuff. So yeah, thanks for the nice presentation. So large language models are usually used in commercially available chat environments. So that is ChatGPT. There is also open source alternatives. The only reacts to input. So if you just have a large language model, it will not do anything. It's not a AI taking over the world. You need to trigger it. You need to run it. And usually what it does is you present an input and it will generate an output. So to some extent, we have the classical input-output setting that we see in many machine learning models. The difference is in the beginning of this elective, we started with numbers, so vectors in, vectors out. Then we talked about images, I think, next. So image in, and then some kind of label, vector, number out. Then we talked about graphs, so graph in, number out. And now we talk about text, text in, text out. Right? And there's all the other different combinations as well possible. So you can also go from text to images. You can go from images to text, so you can describe images. You can go from graphs to descriptions and so on. But most of this is cutting-edge research. So it's not trivial. Not all combinations have been explored. So this is all stuff that is currently happening at the big universities. And of course also at the companies. They are faster than human response time. So if you want to read write an email quickly, they are quicker. If you want to read a lot of text, they are quicker. And if you run it, what you recognize, it looks a bit like it would produce one word after another, right? Because that's the interface. So it's not like one step giving you the whole thingy here. It will give you one word after another word after another. And that impression is actually true. So these models work regressively, autoregressively. So basically what they do is, based on this input, they will first produce maybe the first word. And what they do is, then they take this one, including the first word as an input, and they will suggest or predict the next word, second one. Then they take all of this, including these two, as an input, and they will predict the next one. Okay, so that's what we mean by autoregressively running a model. We run the model, do the next prediction, run the model, do the next prediction, and so on. Okay, now we talk a bit about how does it look inside. So what does it take to build a large language model a bit? And in particular, we talk about tokenization, so a new word, amazing. We talk about embeddings. We talked a lot about embeddings already in the last lectures. So embedding is usually if we create a vector space, so a high dimensional vector describing something that was an image before in a meaningful space, right? So before we were projecting graphs or images to this embedding space. For the molecules, we called that fingerprint. And the idea was two similar molecules should be close in the embedding space. So we will have this concept here as well. We have a transformer architecture that we will talk about, and we talk about training briefly as well. So let's get started. So what is the big problem? The big problem is if we talk to a machine, we communicate with human language, right? So if you're lazy, you want to write your master thesis, you ask ChatGPT, write my master thesis. If you were to build this model, the big problem is that usually a computer understands numbers. So this was a big issue we had also for the previous topics, right? So we somehow need to represent the information we have in a format that a machine can work with it. And in the first lectures, we didn't have that problem because we were talking about numbers to numbers, vectors to vectors. Then we were talking about images, and there we had this issue that we have an image, a matrix on one side, and basically if we have two images of, I don't know, like a car, they might look very different. So the matrix inputs look very different. I can't work with that. Like a machine can't learn from that directly. We need a way to make a meaningful connection to a vector space. And we have that problem here as well, because, well, how do you encode a word right in a vector space such that it makes sense? So that's the main issue we have. And there's a simple solution, and the simple solution is that we cut the example sentence into words. So we say a CSTR and a PFR are reactors. So that's a sentence in natural language we all understand. What we do is we say, hey, this is a word, that's a word, that's a word, that's a word, that's a word. Very simple. And then we add a vocabulary. And do we have an example of the vocabulary? No. Okay. So basically, we have a vocabulary somewhere, and that's kind of a dictionary for a computer. So what does it mean? We say the word CSTR, oh, that's this vector. And the word and, oh, that's this vector here. And the word reactors, oh, that's this vector here. So what you recognize, I'll come to you in a second, what you recognize is basically we have a vocabulary, and we map every word to one vector. And we talked about this, I think, last lecture. So this one is called a one-hot encoding. Okay, so we did that for the atoms in the fingerprint of the GNN, for example. So this one is one way to go from human language to vectors. Why vectors? Because we can process them in neural networks. And you had a question.
Yeah, because words often kind of have minute shapes, for example, for reactor versus reactors. You can't distinguish if one wants to code that.
Yes.
They are, in fact, kind of the same word. So how do you deal with that? Or can you just deal with that through having so much data?
Yes. I think I have an extra slide on that. Yes, perfect. Okay. So I come back to that. So you have a very valid point. There is not only one, there is many problems with this one here. And we come to that, and then we talk about the solution to that as well. But before we do that, I want to make you aware that there is different ways to set up these vocabularies, and that also reflects a bit, comes back to a bit your question. So what we could do is, we could say, hey, let's do one of these tokens, we call that, for each word. The advantage is entire words are captured, and entire words usually have some kind of meaning. The problem is, well, English language has a few thousand words, so these vectors become quite long. That's a bit of a pain. And then, as you mentioned, each change of the word also creates a new token. So if I follow this approach, if I add an S at the end, that will be a new token. So will be a new vector representing that. And I forgot, but English language has 50,000 words around. If you add a few other languages, you get long vectors. And that can be a problem because, well, it's not getting easier to learn from that. There's a different approach. You could say, hey, wait a second. We don't teach words, we teach alphabet first, right? So if you go to elementary school, the first thing you learn is an alphabet. And that is much easier, right? Because we only have a limited number of letters. So now we don't need 50,000 words and vocabularies, we just go for the letters right away. However, then we end up with very long sequences. So every sentence becomes extremely long. because we look at every letter individually. And also we are losing a bit of meaning. So it's a bit more difficult if we have this representation to understand what we're talking about compared to this one here. So there's a trade-off between those. And usually nowadays people find some kind of common ground in the middle. So what they do instead is they work based on frequencies. So you will have an algorithm going through your text or going through an example text in your language. For example, saying, hey, let's pick two letters. So that's the length of my token. And I just count all the combinations happening in my language. And the most frequent ones I choose as potential tokens. And you can do that not only for 2 letters, you can also do that for 3, 4, 5 letters. So basically this just gives you the most common or most frequent sequences of letters in your language. And by building tokens based on that, you can find a good trade-off between this huge vocabulary here and the long sequences here. And this whole process we call tokenization. So from text to a simple vector representation. And good news is this is all established. So by now what you do is you go to Python, you go to, for example, Hugging Face or to another NLP library, and you can find tokenization algorithms out there, and you just use the most common ones. But the general concept is a bit clear. Yeah?